Hi everyone, thank you for joining us for the last day of the AI Blueprints Hackathon workshops. Today we have a workshop from the CoopHive team and the Recall team. So we're going to start off with the CoopHive team. Let me find our speaker.
Okay, so I'm Zheng with CoopHive, and we've been building this framework for modular escrow and settlement. So I'll be basically just explaining like the architecture, and maybe some places how to interact with it, how to extend it. Are you guys familiar with DAS? Are they able to send chat messages? I need to see how much of the audience is already familiar with DAS as an Ethereum attestation service. See if I need to explain that first. I guess I'll go over it in brief. So EAS is Ethereum attestation service, and the core idea of it is just the idea of an attestation, which is one party saying something about another party. So let me find their core data structure. It's this struct attestation. So the way it works is you register a schema with EAS, which is like a type, and then people can make attestations on chain, which is like you putting it's essentially just an object of that type, specified by the schema, and then extra metadata about when it was made, who made it, and you can reference other attestations, and you can attach a recipient field, like attestations are X saying something about Y. So that recipient field is an address. And then there's also the concept of revocation. So maybe some things are only true for a period of time. So after it's not valid anymore, you revoke it. And so, oops. So basically our core abstraction is just an interface. Let me find it real quick. An interface IArbiter, which has a single function check statement, that goes from an attestation and a demand to a Boolean for whether that statement is valid or not in the context of a deal. So I'll walk through a brief example to see, like, to show how this works. So when you have an escrow process, like the basic payment, the basic flow and escrow settlement is the buyer puts an asset into escrow, demanding something from the seller. And if the seller validly fulfills that, then they get to claim what the buyer put into escrow. So in a simple example, the buyer puts ERC20 tokens into escrow. And so we have this ERC20 escrow obligation for the escrow side. And the buyer gets to specify arbitrarily an arbiter and a demand. And this is where the check statement function and the IArbiter interface comes in. And the token and the amount is how much of the ERC20 token they're putting in. And there's other kinds of escrow obligations. So you can also put like ERC721 tokens into escrow, in which case you're transferring the statement data is token and token ID, because ERC721s have a token ID and not an amount. You can put ERC1155s into escrow. You can put bundles of tokens into escrow. You can even put things that aren't tokens. For example, you can make a promise saying, I'll make a certain attestation about you if you fulfill my demand. So we have attestation, escrow obligation. And then the other side of this is modular because of this IArbiter interface. Essentially, the demand side becomes generic, because anything that you can represent as an attestation and for which you can implement a smart contract with this function check statement that takes in the attestation and the demand and says whether it's valid or not, can be used as the counterparty to these escrow obligations. So we already have ones for token payments. So say that you're buying ERC20 tokens for other ERC20 tokens, then you would demand a token payment obligation as the other side. And the way this works is this token payment obligation implements this IArbiter interface. And here we have the statement data of what token, how much, and who you're paying it to. And in the implementation of check statement, in this case, there's no extra type for the demand data because it's identical to the statement data itself. Like you're just demanding how much of a token, what token, to whom. It decodes the bytes, like Solidity has no generic type, so that's why it's bytes. It decodes it as its own demand data, in this case, which is the same as its statement data. It checks if the amount that you actually paid is more than what's demanded of the correct token to the correct person. Returns true if so, returns false otherwise. And the escrow obligation, in collect payment, essentially it does a few checks on the attestation just to see like if it's of the correct scheme, if it's expired, etc. And then there's this check of in the demand you specify the arbiter, so it wraps the arbiter as IArbiter, that interface, checks checks the fulfillment, like the sell side statement against the demand, and you get to collect the escrow if you were the maker of the sell side statement and it's valid. And all of the escrow contracts are implemented like this. So essentially, you can add new escrow contracts just by following this pattern of taking in an arbiter and a demand besides whatever else you're putting into escrow. And then you can make sell side fulfilling, sell side obligations just by implementing that interface check statement. And there could be multiple implementations of check statement for the same kind of statement. And there can also be arbiters that aren't tied to a particular kind of obligation. So like in the example that we give of ERC20 payment obligation, implementing IArbiter and check statement just for itself and checking like the token amounts, this is very specific to this kind of obligation. But there's also some more generic arbiters. So the most basic example is this one that just always returns true. And then maybe you could check nothing about the demand data or nothing about the statement itself, but just who made it. So in this case, this trusted party arbiter, the structure of the demand is it's made, you expect it to be made by a particular party. And this base arbiter based demand thing demonstrates the chaining of demands. So you could say, in addition to some other demand, I demand that this be created by a certain party. And the way that works is, okay, if the statement's recipient, which is the person who made the statement, because it's the contract, it's the obligation contract making an attestation about you saying like, yes, you deposited escrow or like you made this payment through this contract. So yeah, if it wasn't you that made the payment or that made the escrow, it fails immediately, and then if not, it goes through and checks the base statement. And here's another general purpose one, this trusted oracle arbiter, in which case you're the demand that you make is essentially that a particular oracle, as specified by its address, says that the statement is valid. So like maybe the logic for validation isn't on chain. And instead the obligation, like say for example, the sell side the sell side obligation represents like a compute job or something. And you validate the compute job by repeating it, and it's not something that can be done on chain. So you could use ERC20 escrow obligation as the buy side. ERC20 escrow obligation as the buy side. Wait, let me find it. And then token amount is how much you're paying for the compute job. And then for the arbiter and demand, you can specify trusted oracle arbiter and implement some kind of off-chain oracle. Say that like listens to on-chain events for when there are attempted fulfillments to this kind of compute job deal, and then checks the job, and then calls this arbitrate function arbitrate true if it's valid, or calls arbitrate false if it's not valid. And so actually like a lot of jobs, including, I mean, a lot of implementations of a lot of arbiters can be implemented through this trusted oracle arbiter, even for like cross-chain logic, because with cross-chain logic, if you're getting data from another chain, you have to do it via an oracle, and maybe a lot of the logic is happening off-chain, as in like not on the same chain that these contracts are being implemented on. And in that case, you would also just maybe like use trusted oracle arbiter as the arbiter that is being demanded directly, and then you implement the arbiter off-chain. And for the statement too, then like, because this generic function that we have in IArbiter, like really all of this is kind of, it's workarounds to solidity semantics, because maybe in a different language, the way it would work is just that like when you make a demand, you pass in an anonymous function with generics. Like when you think about what a demand is, or what you want to pass into a function when you make an escrow, it's like I will put this into escrow, and then I expect this to be done, and you expect what's to be done as an anonymous function. But because Solidity doesn't have generics and anonymous functions, that's why you have to implement this first as a contract and pass in the address. And so, where was I going with this? Oh yeah, and so IArbiter implementations can be like you can think of it as a partial function, and end to end that's only running on the statement representing the counterparty obligation, and you're partially applying it with your demand. So different implementations of IArbiter represent like different kinds of checks, which could be specialized to a particular kind of statement, or it can be specialized to contexts more general than a statement. Than a statement as in like a particular thing to be traded. And then so as for our bounties for like this Filecoin hackathon, I think like something that would be valuable is extending both the buy side and the sell side of this framework to support things in the Filecoin ecosystem, because like Filecoin as a network for storage, storage is something that can be traded. Like you could both, I guess you could think of it on both sides. You could promise to store something in exchange for something else to be done, and then you can also like sell your storage, as in somebody else says, I'll give you tokens or something for storage, and then you provide the storage. And so it would be valuable to implement both this escrow pattern to have like things on Filecoin, whether that be directly like Filecoin proof of storage or other systems built on top of Filecoin, to be put into escrow, so that anything on the sell side for which check statement is implemented can be exchanged for it, or on the sell side to like create an arbiter in a statement representing something within the Filecoin ecosystem, so that like anything on the buy side, these tokens or like attestations or whatever, can be used to pay for it. And yeah, the nature of statement data itself is like, because the check statement function in IArbiter is just the statement and the demand to a Boolean for whether it's valid or not, like the statement data has to just contain whatever on-chain data is needed for the arbiter to make the decision. And so in some cases, like say if, as with trusted Oracle arbiter or with other Oracle-based systems, most of the logic is off-chain. We have this generic obligation to called string obligation, where it's just a single field string item. And like maybe the way this works is that the arbiter is an oracle, and it's all off chain, so they just read the string and they decode it as JSON or something. Because if it's not an on-chain contract decoding this as a solidity struct, then it doesn't have to be structured. Like it doesn't have to be semantically rich as a solidity struct. And so we have other language SDKs to this as well. Like so, for example, in the Rust SDK, there's special utilities. I mean, it's rather simple to implement, but there's these helper functions to interact with string obligation as JSON with Saturday in Rust. Yeah, so you can treat it as like Rust structs. And also in the TypeScript SDK, there's similar facilities to interact with string obligation as either as JSON data or decoding it with Zod. Or with archetype, or with like, yeah. So treating the data as structured JSON data, because TypeScript doesn't have as canonical of a serialization deserialization solution as Rust with Saturday. So I just supported like two that are like Zod and archetype. And yeah, so to like. In considering how to implement both the obligation and the arbiter, like, I guess the thing to think about is what kind of information does the arbiter need to make the decision? And that's what determines how the statement data and the demand data is structured. And the implementation of the system could be a mix of on-chain and off-chain, and like the structure of the data depends on who needs it where. So it's like if check statement isn't entirely implemented as a smart contract, and all the logic is on-chain, then it needs to be a rich solidity struct with all the information that the arbiter needs. On the other hand, if it's all off-chain, then you could like, yeah, it doesn't have to be solidity struct. It can be data that's easier for the off-chain oracle to handle. And yeah, so with our hackathon bounty, there's like no limitation on exactly where the integration should be done. As in like, it doesn't have to be smart contract, doesn't have to be oracles. So we have deployments on Filecoin and on Base Apolia by default. And there are scripts to deploy it on other chains as well. And so like maybe if these were on Filecoin itself, a lot of the logic could be on-chain, but then if we're on Filecoin itself, you're also limited in the escrow contracts with like ERC20s, ERC721s, ERC1150s, whatever, to only be trading tokens that are on the Filecoin chain. Whereas like the contracts interoperate within chains, and like it's all solidity. So nothing has to change in deployments between chains, but you can't specify as an arbiter and as a demand something that's like a contract on another chain. And so to support that, then like maybe that's another avenue of development to make these like cross-chain bridges so that you can actually interact with arbiters, or with counterparties with like the other side of when the other side of the deal is on a different chain. And like thinking about it immediately, I think that this would probably have to be done pretty case by case. So like wrapping something within Filecoin so that it can be interacted with from any other EVM chain is like, yeah, like that's another potential project. I mean, I guess that's about it for the architecture. And like so far, the core contracts just have facilities for using like the standard ERC20, or I mean, yeah, the standard token standards ERC20, ERC721, 1155, and then bundles of these as both the buy side, as in like putting it into escrow, and sell side, as in fulfilling an escrow, as well as attestations on the escrow side, as in like I'll make this attestation about you. if you fulfill my demand. And then in the core of the arbiters, the general purpose arbiters implemented are this for checking, one for checking like that the counterparty is exactly a particular attestation. For like when you already, maybe you've already settled the deal off chain and you're just like finalizing some kind of transfer on chain, and you don't actually need any logic. You just know like only this particular attestation can claim the payment. That's what this is for. This trivial one that always returns true, useful as like a final base for when you're training them together, with like when you're adding additional parties with these kind of layered ones that take a base arbiter and a base demand. And then this Oracle-based one, and then this one that checks if it's from a particular creator. And the code base is on GitHub at github.com/CoopHive/Cosmos. That's about it. Does anyone have any questions?
Hello, we had some questions in the questions tab. If you see down below, next to the chat, there's questions.
Composable agreements in real world scenarios. Okay, yeah. Yeah, sure. I can demonstrate like how this is used in the tests. So yeah, one example is you want to buy ERC20 tokens for other ERC20 tokens. I mean, you can do this on exchanges, but this is like atomic. And you could add additional demand to this, like if you want to just buy tokens from your friend or something, deposit your tokens, your bid tokens, like say that you have USDC and you want to buy EURC, then you deposit USDC into escrow and you demand EURC, and they give you EURC. So yeah, you make the escrow, they make the payment, and then that settles. And then you could see though, like with what I said, you can demand not just certain amount of EURC for USDC, but a certain amount of EURC from a particular party, or like given it meets other conditions. Like say that you wanted to demand it from just your friend and you don't want anybody else to fulfill your bid, then you'd use this trusted party arbiter demanding that like the fulfillment be from a particular creator, and then as the base arbiter and as the base demand, you demand the same thing that you demand in the base case where it can be from anybody, which is the ERC20 payment obligation itself's implementation of check statement. And then another case, I think this is the other test for like a demonstration of buying a compute job with ERC20 tokens. There we go. Oh, I was looking at the Rust test. I mean, using it from an SDK. If you want to demand a compute job, you can. I mean, this is in the test, so if you want to read this more in depth, it's in. I'll send the link to this as well. Yeah, if you want to buy a compute job for ERC20 tokens, you make your, like, in this case, we're just demanding that a string be capitalized, but in the real world, like say this could be a Python script that you expect to be run, or a Docker file or something. You can put this on chain with your escrow, make your escrow, and then the sell side decodes your demand, runs the job, which is just this line. Like this line in real life would be like actually executing your job, whether it be like building the Docker container and running it, or like running a script or whatever. And then puts your result back and claims your tokens. But like the interesting thing here is that you could, like what you demand of the fulfillment is generic. And so in this case, the arbiter that we used is just the trusted party arbiter, like maybe like existing existing DCNs, decentralized computing networks, already usually work like this, where it's just that particular sellers are trusted, and so you could, like, if you settle a particular address to claim your payment with trusted party arbiter, but then in a more complex case, like say that you have a particular strategy, say whether it's like a particular oracle executing in a TE or optimistic mediation or something, you could just swap out the arbiter, and the rest of the structure of the deal remains the same. You just demand a different arbiter with different demand data, and now instead of just the particular person that you said you trust to fulfill your job being able to fulfill it, it's anybody can fulfill it, but you trust it to be correct because there's actual validation systems in place. And you could also, like, for the same kind of demand, you could choose different validation systems. Like in the same example of a compute job, maybe there's one case where like it's that every job is run by two different people, and it only validates, like, check statement only validates true if the two people submit the same thing. But maybe this is more expensive. So then in case you don't need that degree of guarantee on your job results, maybe there's another one that's like probabilistic. Like at some rate, your jobs are checked, and then if it gets checked and it fails, it's not valid, and otherwise it is. And so in this case, like maybe some faulty jobs get let through, but it's cheaper. Any other questions?
I guess one of the things people are really interested about is use cases and what you really want to see. So I think people are looking for what you and the CoopHive team are really wanting to see from people out of this hackathon.
Yeah, use cases would be like, so the two places to extend are like adding more adding more obligations. So there's two kinds of obligations, like those that involve escrow, buy-side obligations, and sell-side obligations, payments. And currently you can buy with tokens, or you can buy by saying like, I'll make this attestation about you, and you can sell in tokens. And there's a lot of stuff in the Filecoin ecosystem that could be used as like as buy-side and sell-side. So like in the example I gave of buying compute jobs, like you could also buy storage. And then there's a lot of different ways that storage can be represented. And then, so it's like, there's not just one solution of what buying storage means. Like maybe it's a different thing to like buy storage as in anything that Filecoin has proved is stored, versus like buying particularly storage on a particular, on a particular extension of a Filecoin, like buying storage on a Kave or Storacha or something. Or even like building something akin to a Kave or Storacha, where it's like you're buying storage available at a particular endpoint, but you like not from an existing provider. It's that like a particular arbiter like validates properties of the storage, maybe by like pinging it occasionally or something to make sure that it's actually there. So yeah, like what we mostly want to see from the hackathon is just extending the ecosystem, implementing these like arbiters and obligations into the Filecoin ecosystem.
Nice. I hope that people have found those sort of examples and what Zheng has just told us about what they're hoping to see. I hope you found that useful, because Mohammed said that it feels quite abstract, so maybe some more research and reading the repo and kind of better understanding it will help. So the links are in the chat, so make sure that you're going back and looking at them. Do we have any other questions for Zheng now? I think no one is typing, so possibly not. In which case, we will end the CoopHive workshop here. And thank you everyone for coming. We have the recall workshop happening in 15 minutes. But before that, we'll have a short break. So feel free to get up, stretch a bit, get a cup of tea, maybe some lunch, depending on what time it is where you are. And we will be back in 15 minutes for the second workshop of today and the last workshop in the AI Blueprints Hackathon workshops. So thank you, Zheng, for joining us today, especially because I know it's quite late at night for you. We really, really appreciate it, you giving us your time. So I will close the screen for now, and we'll be back very soon.